The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Thank you very much, Dimitri and Shalek, for putting this nice session together. And thanks a lot for putting me after Joe. He really introduced the subject very, very well. His title and my title are not the same, but we're both talking about the same message. So what I was asked to talk about today is robustness of SCC incorporating an admixture. And just a disclaimer, not all admixtures behave the same way, as Joe said. But as you know, SCC is not always a very robust material, and that is one of the obstacles of penetrating markets, especially for cast-in-place applications. You have here two pictures, so they're both SCC, and they're not neither of them is a perfect SCC, yet they are both SCC. And Joe told us what happens if you increase or decrease water or superplasticizer. You get into segregation issues. You get on the right side, on the left side, you get into very stable concrete, but not enough passing ability. So neither of them is a successful SCC. So the approach here is to look at what happens when we use viscosity-enhancing admixtures to increase the viscosity, to increase the robustness. And you can think about it as this box of sweet zone that Joe was telling us about, which is where yield stress and plastic viscosity meet to make the concrete both having high passing ability and high stability. So if you look at two mixtures over here, mix A is more robust. In other words, you can vary the proportioning of whatever material you have here. Let's call it superplasticizer from X minimum to X maximum and still meet the requirements that are specified to ensure that your concrete has SCC workability. Versus mix B, it has a very sharp curve, and if you deviate from the optimum point a little bit, then you get into trouble. And it's been known that SCC, or the use of viscosity-enhancing agents or viscosity-modifying admixtures, when you use it at a low dosage, can help you enhance this robustness and widen that zone. So here, as you'll see in my presentation, the viscosity-enhancing admixtures are not really used to enhance stability, but to enhance robustness. So I'd like to talk to you a little bit about the various superplasticizer and the viscosity-enhancing admixtures that were used in this study, and look at some of the methodology. And here we're proposing two approaches to evaluate robustness, and look at what are the test methods that are required to qualify or to quantify robustness. So in terms of viscosity-enhancing admixtures, we use 5 of them in different combination with superplasticizers. So you have a PS1 would be a diatom gum. So this is a polysaccharide. And PS1 and PS2 are the same, except the difference is that they are ground at a different fineness. So PS1 in maximum apparent diameter would be relatively coarse. So if this would be cement, your 75 micron would be about 80%, 90% of the cement. So the 75 is finely ground, so it goes into solution faster than the PS1. PS3 is a whaling gum, which is also a polysaccharide, different chemistry, also coarsely ground. And then you have the cellulosic base material, it's HPMC. Hydroxymethyl cellulose, and then modified starch. All of those are used as viscosity-enhancing admixtures to modify rheological properties of cement-based materials, including SCC. The concrete mixture that was used in this study is already a very stable concrete. So if you look here at the water-cement ratio, is already low, and we know by reducing the water-cement ratio, you can increase stability, viscosity for a given slump flow or yield stress. We adjusted the, so 14 millimeter half-inch aggregates, PNS and PC Those are the dosages that you see that are required to give you the slump flow that is the reference slump flow. And the viscosity-enhancing admixtures, they varied between 0.02% to 0.05% by mass of water, so it's 200 to 500 ppm. And the dosage is adjusted for one criteria, and that is to secure a surface settlement less than 0.5%. Joe shared with us that the column segregation test, the surface settlement test is another test, and all the dosages were there to secure that, and the dosages are relatively low because the concrete is already stable. In terms of combinations, we had 8 different combinations. So the PNS is used with the diatom gum and the whaling gum at different fineness, and the polycarboxylate ether is used with the diatom gum. It is not compatible with the whaling gum, and it is also used with the cellulosic material and with a modified starch material. And then for the first phase of the study, we changed the water content. So this is to simulate the moisture content of the sand, and that's a big problem in quality control of the moisture content in the production of SCC. So here we had concrete that the reference would be concrete that has been proportioned at surface saturated dry conditions for the sand. And in this case, you have -1%, so you assume you made an error in estimating the moisture content. And if you figure out what the water cement ratio would be, it will drop from 0.37 to 0.35. And if you could increase the moisture content of the sand 1%, that would be 0.39. So you go through the same exercise with all the different combinations. And the phase 2, it was undertaken to evaluate the errors that you would make in the proportioning of the superplasticizer. So it was plus or minus 10% of the targeted value. And phase 2 was done with 2 concretes, with a PNS and a VEA compatible, the same thing with polycarboxylate, versus the first one was done on all the combinations of VEA and superplasticizers. Now, in terms of properties, we were very aggressive. We did a lot of different properties, concrete, slump flow retention, air volume retention, T50 retentions, etc. And then the J-ring. So Terry is not here. We did not do the L-box, thank God. Portable vein. So this is a thixotropy, a structural buildup at rest, inclined plane, as well rheometric tests. And of course, the mechanical properties of the concrete. So many different concrete mixtures, but also many properties. And that had all these tests had to be done at the same time, because if you're doing something where time is important, like Chelik said, especially in this case, so you have to mobilize a lot of people to do these tests. And the majority of these tests, of course, are field-oriented tests. So thixotropy, if you take one of the test methods, this is a surface settlement, and look at the surface settlement. As Joe said, if you reduce the amount of, in this case, the sand humidity, you can still have 0.6, 0.65. This is the target value. But if you do not make adjustment for extra water, then your surface settlement is going to increase. So you can look at, this is concrete without any viscosity-enhancing admixture, PNS, and these are the PNS with the different viscosity-enhancing admixtures. One thing you see that, first of all, the settlement is less than 0.5, which is the target value. And the second thing is the response is pretty flat. So it tells you that these concretes are more or less robust. On the other hand, if you take sand humidity versus, in this case, yield stress, using a rheometer after 25 minutes, the polycarboxylate without any VEA is the blue one, and you see there's a very sharp reduction in yield stress when you increase the water content from the sand, and when you do the viscosity-enhancing admixtures, depending on the combination, you can still have a sharp reduction or more or less attenuated response. And that's what you're looking for. So the approach here was to look at the coefficient of variation, standard deviation divided by the average. And here are the different responses, and I'm not going to go through them, but these are the 8 mixtures. And for each of these mixtures, for each of the responses, we determine the coefficient of variation, standard deviation divided by the average, and we simply rank them between 1 and 8. 1 is the lowest coefficient of variation, and 8 would be the highest coefficient of variation. So you go through that. This is here the T50, J-ring, slump flow using a cylinder, air content, etc. Surface settlement. Again, this is 1, this is 8. And so on and so forth, mechanical properties. And then at the end, you have 20 of these values. And you take a sum of the ranking. And then using a formula over here, you have normalized sum of the ranking. So the sum of the ranking that are the lowest, you have it as 1. And the highest would be at 8. And then using this formula here, the normalized sum of the ranking, you basically put it in percentage. And you see that the highest normalized sum of the rankings, for example, 175%, are the mixtures here. So let's look at the one that is performing very well is the PNS and the diatom gum at 75 micron. This is the one that is very fine, followed by the PNS with the Wayland gum and the PNS with the diatom gum that are coarser, and so on and so forth. If we look at the bottom here, we see the PNS without any viscosity admixture was less robust, and the polycarboxylate by itself was the least robust. And then we developed some recommendations of what we consider to be high robustness, very high robustness, medium robustness, low robustness. So again, if you have a project, you can go through an exercise similar to this and measure all 20 properties, which I don't wish for you to do. And that's the second part of my presentation, and then determine where you are. So that's one approach. The second approach, we adopted it in the second phase where we looked at the variability of the superplasticizer dosage. And again, this is plus or minus 10% of the optimum value. And here we adopted another approach. So surface settlements, so for example, here, this is the value. If you increase superplasticizer, you're going to increase the settlement, less stability. You reduce it, you enhance settlements. We adopted an approach where we decided on what would be the upper limit that you would not want to surpass for each property, and the settlement, we decided that the upper limit from the target value should not exceed 10%. So by looking at the low value and the high value, you can take this distance, B divided by A by percentage, and you call that rate of acceptance. So the higher rate of acceptance, the more robust the concrete. In this case, the rate of acceptance would be 100%. That is, regardless of the superplasticizer, you are always below that target level. And in some values, you have a lower limit. For example, over here, this is a slump flow after 10 minutes. So your value at SSD condition would be 630. If it's SSD plus 10% SP is 650. And this is should be the upper limit, or lower limits, and then 600, 610. And then if you reduce the super, you are beyond that. And if you look at this, B divided by A, etc., you will have a rate of acceptance that is lower. So those are the values that we determined. For strength values, we said we should be maximum deviation of 5% of mechanical properties, slump flow 3%, settlement, you saw it there 10%, 5%, etc. I'll just give you two examples here. This is the one we just looked at. So if you look at this, it's 84%. So from minus 10% to plus 10%, 84% of the cases, you are within the minimum limit that is set over here of 600 mm slump flow after 10 minutes. And then if you look at all the values, mechanical properties, fresh properties, the two mixtures that we did, the PNS plus the Wayland gum, and the polycarboxylate plus the diatom gum, both of them at 180. So the higher the values would be, would reflect that the concrete are more stable. If you look at the average, they're very similar, 81 and 77%. And those were picked up because they were the two approaches that were more or less gave us the highest robustness. So you can compare this approach, coefficient of variation versus the rate of acceptance, and I think both of them are acceptable in terms of quantifying robustness. So in case you do not want to do all these 20 properties, we did some statistical work, and I invite you to consult that. This was published in ACI Materials Journal back in 2011. This work was done as part of a master's study of C.O.V Naji at the University of Sherbrooke at the time. And through statistical analysis, Kendall coefficient of concordance, etc., we determined that you can really mimic, as if you were doing all these properties, to look at the degree of significance of detecting the robustness by reducing this to 11 properties. And still 11 properties is a lot, so through more statistical approach, we determined that the most significant parameters are those 11 listed here. But if you want to limit yourself to 3 parameters, we recommend that you would look at the yield stress of the concrete at rest, so an indication of thixotropy of the concrete after 25 minutes of rest. And Gil showed us what happens if you waited 20 minutes without pumping. Surface settlement, indication of the stability of the concrete, and a 28-day compressive strength. So you can go from 20 to 11, and if you really want to be stingy and don't spend a lot of time on testing, you can even go with 3. So what we see as conclusion is SCC, and again, these are stable SCC mixtures to start with, made with PNS, and this is a type 1 cement, were more robust than the polycarboxyl ether that we are using. And when we use a viscosity-enhancing admixture, in all cases, we enhance robustness. Those that were made with polysaccharide, the diatom gum and whaling gum, were more robust than the modified starch and the cellulosic admixture that we used. And again, I showed that there are 2 approaches for evaluating robustness. Both of them work equally well. And then the 20 approaches to a 20 test method, you can take it down to 10. And if you really want to take it down only to 3, you can select to look at that, or any variation between those 3 and 10. And that should give you an indication about the robustness of your concrete. With that, I thank you very much.